Hi friends, today I am giving a lecture on Hamiltonian cycles in backtracking. So Hamiltonian cycle problem is one of the application of backtracking. So what is Hamiltonian cycle? How to find out Hamiltonian cycles for a given graph? So we can take some example graphs. We can find that any Hamiltonian cycles are exist in that graphs or not. We have to learn these topics in this video. So first of all, what is Hamiltonian cycle? So suppose we can take a graph. So graph G. So G is equal to V comma E. So where V is the set of vertices and E is the set of edges. So the given graph is a connected graph with n vertices. So what is connected graph? Connected graph is nothing but we can take any pair of vertices among n number of vertices. There exists a path between that pair of vertices. Suppose we can take this graph. So we can take this pair 3 and 6. There is a path between these vertices. So how to go to 3 to 6? So 3 to 4, 4 to 5, 5 to 6. So now we can take pair 4 comma 8. So there is a path between vertex 4 and vertex 8. So 4 to 5, 5 to 6, 6 to 7, 7 to 8. So that is nothing but we can take any pair of vertices in a given graph. So that pair of vertices are connected by using a path. So then that graph is called as a connected graph. So for finding out Hamiltonian cycle, the given graph G is equal to V comma E is a connected graph with n number of vertices. A Hamiltonian cycle is a round trip path along n number of edges that visits each and every vertex exactly once except the starting vertex and ending vertex and returning to the starting vertex where we are starting. So then this is called as a Hamiltonian cycle. Suppose we can take a graph. So we can start at any vertex from the given graph. So suppose we are starting at vertex 1 or we are starting at vertex 2 or we are starting at vertex 3 or we are starting at vertex 4. So we are starting at any vertex from the given graph. Generally, we are starting at first vertex. So now we are starting at the first vertex. Now we are starting at the first vertex. So we are starting at vertex 1. Next, we are going to the vertex 2. Next, we are going to the vertex 8. Next, we are going to the vertex 7. Next, we are going to the vertex 6. Next, we are going to the vertex 5. Next, we are going to the vertex 4. Next, we are going to vertex 3. Next, we are going to vertex 1. So, this is the Hamiltonian cycle for the given graph. The path is 1 to 2, 2 to 8, 8 to 7, 7 to 6, 6 to 5, 5 to 4, 4 to 3, 3 to 1. So this is the Hamiltonian cycle for this graph. So except first vertex and last vertex, the remaining vertices in the given graph visited exactly once. So suppose we can take at vertex 4. So what is the Hamiltonian cycle for this given graph? So vertex 4, next go to vertex 3, next go to vertex 1, next go to vertex 2, next go to vertex 8, next go to vertex 7, next go to vertex 6, next go to vertex 5, next go to vertex 4. So this is the example for we are starting at vertex 4 and returning to the vertex 4. The remaining vertices in the given graph visited exactly once. So this graph contains, this is one Hamiltonian cycle and this is another Hamiltonian cycle starting at vertex 4. So now we are starting at any vertex in the given graph for finding out the Hamiltonian cycle. Next, suppose we can take this graph. This graph contains any Hamiltonian cycle or not. So this graph does not contain any Hamiltonian cycle because this graph contains a vertex. This vertex is called as junction point. So if any graph contains this junction point, so that graph does not contain Hamiltonian cycle. So this junction point or junction vertex is also called as Hamiltonian, also called as articulation point. So suppose if the graph contains any Hamiltonian cycle or not, we are checking. So we are starting at vertex 1. Next we are going to vertex 5. Next we are going to vertex 2. Next we are going to vertex 4. Next we are going to vertex 3. Next we are going to vertex 2. But so vertex 2 is visited second time. Okay. Because it contains only a single path to go to vertex 1. So because of that reason, this graph does not contain any Hamiltonian cycle because vertex 2 is visited 2 times. So returning to the starting vertex. So this graph does not contain any Hamiltonian cycle. So this graph does not contain Hamiltonian cycle. Hamiltonian cycle. Next, suppose we can take this example graph. So this graph also does not contain any Hamiltonian cycle because here vertex 3 is a junction point. So this vertex is called as articulation point. If any graph contains articulation point, so then we can say that this graph does not contain any Hamiltonian cycle. Check whether this graph contains any Hamiltonian cycle or not. So suppose we are starting at vertex 1. Next we are going to vertex 2. Next we are going to vertex 4. Next we are going to vertex 3. Next we are going to vertex 6. Next we are going to vertex 5. Next we are going to vertex 3. But vertex 3 is visited 2 times, but it is not a starting vertex. So because of, according to the definition of Hamiltonian cycle, so each and every vertex visited exactly once except the starting vertex and ending vertex. So starting vertex and ending vertex is same. So this is vertex 1. But so vertex 3 is visited 2 times. So then we can say that this graph does not contain any Hamiltonian cycle. So vertex 3 is called as a articulation point. So what is articulation point? So suppose we are removing this vertex. This graph is divided into two subgraphs. So by using which vertex, the graph is divided into two subgraphs. So then this point or this vertex is called as articulation point. So articulation point is nothing but it is a vertex. By removing this vertex, the graph divided into two subgraphs. So then that point or vertex is called as articulation point. So here vertex 3 is called as articulation point. By removing this vertex, so we have two subgraphs. The first graph contains 1, 2, 4. The second graph contains 5 and 6. So the graph is divided into two subgraphs. The first graph contains only vertices 1, 2, 4. The second graph contains only two vertices, vertex 5 and vertex 6. Then, so this vertex is called as articulation point. Next, suppose we can take this graph. So this graph contains any Hamiltonian cycle or not. Suppose we are starting at vertex 1. Next, we are going to vertex 2. Next, we are going to vertex 4. Next, we are going to vertex 5. So then we have to return to visit vertex 3 and vertex 6. So suppose we are returning from vertex 5. So we are visiting the vertex 4 second time. So according to the definition of Hamiltonian cycle, each and every vertex visited exactly once except the starting and ending vertex. But vertex 4 is not a starting vertex, is not a ending vertex. But this vertex is visited 2 times. So then this graph does not contain any Hamiltonian cycle. Now we have to check another way. So we are starting at vertex 1. Next we are going to vertex 3. Next we are going to vertex 4. Next we are going to vertex 6. So here there is no path except the incoming path. So then we have to return from vertex 6 to vertex 4. But vertex 4 is visited 2 times. So then we can say that the graph does not contain any Hamiltonian cycle. So here vertex 5 and vertex 6 are called as pendant vertices. So vertex 5 and vertex 6 are called as pendant vertices. So if any graph contains pendant vertex, so then thus the graph does not contain any Hamiltonian cycle. So G3 and G4 does not contain any Hamiltonian cycle. Does not contain any Hamiltonian cycle. Any Hamiltonian cycle. Because here the graph G3 contains articulation point. So because of that reason, the graph does not contain any Hamiltonian cycle. Consider graph G4. This graph contains a pendant vertex. If any graph contains a pendant vertex, that we can say that the graph does not contain any Hamiltonian cycle. Next, consider graph G5. So we have to check whether the graph contains any Hamiltonian cycle or not. So suppose we are starting at vertex 1. Next we have to go to vertex 2. Next we have to go to vertex 3. Next we have to go to vertex 7. Next we have to go to vertex 6. Next we have to go to vertex 4. Next we have to go to vertex 1. But there is no visiting of vertex 5 according to the definition of Hamiltonian cycle. So we are visiting each and every vertex exactly once, but vertex 5 is left. So then we can say that this graph does not contain any Hamiltonian cycle. We have to check another way. Suppose we are starting at vertex 1. Next we have to go to vertex 5. Next we have to go to vertex 6. Next we have to go to vertex 7. Next we have to go to vertex 3. Next we have to go to vertex 4. Next we have to go to vertex 1. But here vertex 2 is left. So we can say that this graph does not contain any Hamiltonian cycle. So G5, graph G5 does not contain any Hamiltonian cycle. Any Hamiltonian cycle. Next, we have to check whether graph G6 contains any Hamiltonian cycle or not. We are starting at vertex A. Next, we have to go to vertex B. Next, we have to go to vertex F. Next, we have to go to vertex E. Next, we have to go to vertex D. Next, we have to go to vertex C. Next, we have to go to vertex A. So A, B, F, E, D, C, A. So A, B, F, E, D, C, A. So each and every vertex visited exactly once except the starting vertex and ending vertex. So this graph contains a Hamiltonian cycle. So these are the examples for Hamiltonian cycle. Graph G1 contains a Hamiltonian cycle. Graph G2 does not contain any Hamiltonian cycle because vertex 2 is a junction point. So if any graph contains a junction point, so that graph does not contain a Hamiltonian cycle. Next, consider graph G3. So here the graph G3 contains one single vertex, that is vertex 3. It is a articulation point. So by removing this vertex, the graph is divided into two subgraphs, that is 1, 2, 4. It is one graph. 5 and 6, this is another subgraph. So if any graph contains a articulation point, that graph does not contain any Hamiltonian cycle. Next, consider graph G4. This graph does not contain any Hamiltonian cycle because this graph contains two pendant vertices, that is vertex 5 and vertex 6. So we can say that if any graph contains a pendant vertex, the graph does not contain any Hamiltonian cycle. Next, we have to go to graph G5. Graph G5 does not contain any Hamiltonian cycle. Here vertex 4 is a junction vertex. So we are considering this junction vertex. So vertex 5 is left or vertex 7 is left. According to the definition, each and every vertex visited exactly once except the starting vertex and ending vertex. Now consider graph G6. So this graph contains a Hamiltonian cycle. This graph does not contain any articulation point or any pendant vertex. So then we can say that the graph contains a Hamiltonian cycle. So this is a Hamiltonian path. So Hamiltonian circuit A, B, F, E, D, C, A. So this graph G6 contains a Hamiltonian cycle. So Hamiltonian cycles start with any vertex in the given graph. So generally we are starting at vertex 1. Suppose we can take a graph. how many number of Hamiltonian cycles are exist for the given graph. So that can be represented by using a state space tree. Now we have to find out how many number of Hamiltonian cycles are there for the given graph. So that can be represented by using state space tree.